Hello students, so today we are going to study about solid state, okay? So you all must be aware about this three states of matter, which are solid state, the liquid state and the gaseous state. And today we are going to talk about the solid state, okay? So let's look at our first slide. We are going to talk about the general characteristics of solid. Now, first of all, the solids have definite mass, volume and shape. Look at this diagram. If we put a solid in this container, if we put a liquid in this container, and if we put a gas in this container, okay, so you can see the difference. The shape of the solid will be the same as it is outside this container, but the liquid will take the shape of the container, okay, and same is the case with the gas. But if we put this liquid in a different shaped container, suppose if we put this liquid in this container, so it will take the shape of this container and will change its shape. But if we do the same thing with this solid, if we put this solid in this container, will the shape of the solid change? No, definitely not. It will not change its shape with the shape of the container, okay? Until and unless we apply pressure on a solid, it will not change its shape, okay? If we take the example of a plastic bottle, suppose if we are having any plastic bottle, this is the plastic bottle, okay? If we are not applying any pressure, so it is having a definite shape. But if we apply a pressure on it, if we apply pressure from both the sides, then it will definitely deform itself and it will change its shape. So the solids have a definite shape without applying any pressure on them, okay? If we apply the pressure on a solid, it will definitely change its shape. Now look at the next point. Intermolecular distances are short in solids. The distances among the molecules which constitute a solid are very short. Look at this diagram now. The A part is showing the particles in solid, okay? You can see here how compactly the particles are arranged. The intermolecular distances means the distance between the two molecules. These distances are very short in solids, okay? And when we talk about the liquids and gases, these intermolecular distances are larger. And since the intermolecular distances are short in solids, the intermolecular forces are very strong in solids. That's why it is very difficult to break any solid. We require a lot of pressure to break a solid, okay? Because the intermolecular forces are very strong. Now the next point is their constituent particles have fixed positions and they can oscillate about their mean positions. Okay, so constituent particle means the particles which will form a solid. They can be atoms, they can be molecules, or they can be ions. Okay, now they have the fixed position, they will not change their position. Suppose this is a solid, this is any molecule, it will not change its position, okay? It will keep on oscillating about their mean position only. Now the next point is the solids are incompressible and rigid. Again I will say the solids are incompressible and rigid without applying any pressure on them. But if we apply any pressure on any solid, they will be compressed, and they can be compressed, okay, by applying pressure. But without applying any pressure, the solids are very rigid and incompressible. I hope the characteristics will be clear to you. Now let's move to the types of solids. Now, based on the arrangement of constituent particles, solids are classified in two types. First one is the crystalline solid, second one is the amorphous solid. So how our constituent particles are arranged, they will differentiate between crystalline solids and the amorphous solids, okay? Now first point is a crystalline solid usually consists of a large number of small crystals, each of them having definite characteristics geometrical shape. Means a crystalline solid have definite geometrical shape, okay? When you will look at NaCl, this is the example of crystalline solid. example of crystalline solid. So when you will look at its structure here, these green balls are representing the Na plus ions and these silver are representing the Cl negative ions. So the Na positive ions and the Cl negative ions are arranged in a particular geometrical shape. They are having a particular arrangement followed in a 3D. Okay, so it is called a crystalline solid. Moving to our next slide, the arrangement of constituent particles in a crystal. The arrangement of constituent particles in a crystal is ordered and repetitive in 3 dimensions. Okay, there is a particular arrangement, or we can say there is a particular order which is repeating itself in the 3 dimensional. Look at this diagram. This is representing our crystalline quartz. Okay, quartz is also the example of crystalline solids. So first of all, there is a small ion, then a larger ion, then again a small ion, then a larger ion. Means a particular arrangement is repeating itself, and this whole 3 dimensional arrangement is made of the same repetitive arrangement. Okay, so we can say that the crystals have long range order. This is important point. The crystalline solids have long range order, means the regular pattern of arrangement of particles repeats itself periodically over the entire crystal. The whole crystal is having a particular arrangement. Okay, now the example, sodium chloride and quartz are the typical examples of crystalline solids. What is quartz? Quartz is a silica oxide, we can say. Quartz is made of silica oxide. Okay, so it is example of crystalline solid. Now moving to our next slide, here are the amorphous solids. So an amorphous solid consists of particles of irregular shape. The particles which are forming the amorphous solids are having irregular shape. They are not having a regular shape. You can see here the arrangement of constituent particles in such a solid has only short range order. When we were studying the crystalline solids, we have studied about the long range order, but here in amorphous solids they are having short range order. Means a particular arrangement is repeating over very small distance. Look at this arrangement. This arrangement is repeating over this much distance only. After this, a different arrangement is there. This is having a space between them. These two are having some small space, then these two are having larger space between them. So a particular arrangement is repeating over very short distance. That's why they are short range ordered. Now the examples are glass, rubber and many plastics. Okay, next point is crystalline solids have sharp melting point. Why crystalline solids have sharp melting point? Suppose this is a crystalline solid. I have told you that they are having a regular arrangement, means the bonds will be having a regular pattern. They all must be having a same bond length, so they all must require the same energy to break their bonds. So if we apply a particular temperature, then all the bonds will be broken at the same time. They will not require a range. They will require a particular sharp temperature at which all the bonds will break at a particular time. Okay, that's why the crystalline solids have sharp melting point. But if we talk about the amorphous solids, some of the bonds will be larger, some are smaller, then others are larger, then there will be some double bonded atoms also. So all the bonds will require different temperature. They all will not break at a particular temperature. This is the larger bond, so this will require low temperature, whereas the double bond will require high temperature. Means the amorphous solid will require a range of temperature. Okay, They will not break at a sharp temperature or at a particular temperature. They will have a range of temperature to be they will require a range of temperature to be broken. Okay, so amorphous solids soft amorphous solids soften, melt and start flowing over a range of temperature and can be molded and blown into various shapes. Or and the amorphous solids can be molded into different shapes too. Okay, now look at next slide. Amorphous solids have the same structural features as liquids and conveniently regarded as extremely viscous liquids. What are viscous liquids? Viscous liquids are those liquids which have the ability to flow, but they will flow at a slower rate. Okay, they will be flowing, but they will flow at a slower rate. There will be some resistance to be there will be some resistance which will be there when they will flow. Okay, so they will flow with some resistance. So honey can be the example of viscous liquid. Because it is also having the ability to flow, but it flows with some resistance. Okay, so amorphous solids have that ability like liquids. Like liquids, amorphous solids have a tendency to flow, though very slowly. Therefore, sometimes these are called as pseudo-solids or supercooled liquids. So amorphous solids can also be called as supercooled liquids or pseudo-solids. Okay. Now the next point is amorphous solids are isotropic in nature. This is very important point. The properties such as mechanical strength, refractive index and electrical conductivity etc. are same in all directions. So when we were talking about amorphous solids, we have discussed that they are having irregular arrangement. You can see in this diagram. There is irregular arrangement of particles. Okay, so when you will move in this direction, A, B. When we will move in this direction, the arrangement of particles is random. Okay, so the property here will be the same as this direction, CD direction. If you move here, the arrangement of particles will again be random. So the properties in all the directions, if we move here, if we move in this direction, the properties will be same in all the directions. Okay, isotropic means, iso means same, tropic means direction. Means the properties will be same in the different directions. Okay, this is the case with the amorphous solids. But if we talk about the crystalline solids, so in crystalline solids, the anisotropic is the nature for the properties. Anisotropy means the properties in this direction, CD direction, will be different from the properties in AB direction. Why? Because in AB direction you can see the arrangement of particles is different than in CD. So the properties will be different in both the directions. Okay, I hope this point will be clear to you. If we move in this direction, the properties will be different. If we move in this direction, the particles through which we are measuring the properties are different. In this direction, the particles through which we are measuring the property is different. Okay, so the properties are different in different directions for crystalline solids. Now moving to our next slide. Crystalline solids have definite heat of fusion, whereas amorphous do not have definite heat of fusion. The reason will be the same, that the bonds in the crystalline solids will be the same. They will require a particular temperature, whereas in amorphous solids they will require a range. So they will not have a definite heat of fusion. Now some differences between the crystalline and amorphous solids. We have already studied this. Let's revise once again. The crystalline solids have a regular arrangement of particles, whereas the amorphous are completely random arranged. So, in amorphous solids, the particles are randomly arranged, whereas in crystalline solids, the particles have a regular arrangement. Now, crystalline solids have different physical properties in different directions. We have studied this earlier, and the amorphous solids have physical properties same in all the directions. The physical properties will be same in all the directions. The melting point is very sharp in crystalline solids, whereas in amorphous solids they do not have sharp melting point. This diagram is showing the heat of fusion. Heat of fusion is the heat which is required to break the solid bonds and to convert the solids into liquids. We can also call it as latent heat. So the solids are having particular intermolecular forces of attraction. The forces of attraction are strong. So when we provide a particular heat, they are regularly arranged in crystalline solids. They will break at the same time and they will be converted into liquid. So the heat of fusion is definite in crystalline solids. Now moving to our next slide. Besides crystalline and amorphous solids, there are some solids which apparently appear amorphous but have microcrystalline structures. These are called polycrystalline solids. So polycrystalline solids are basically those solids which appear like amorphous but actually they have the crystalline structure. And we can't call them as crystalline solids because they are not crystalline. They are made up of crystals, but so they are called as the polycrystalline solids. These are the polycrystalline solids. Okay, the arrangement is not regular here, you can see. So we can't call them as the crystalline solids. The polycrystallines are solids that are composed of many number of small crystals. These are arranged in different orientations and are bounded by highly defective boundaries. So as we were talking, they are not regularly arranged. They are having different orientations in different directions, and they are having some defective boundaries too. Okay, so these are not crystalline solids, but they are made of small crystals, and the crystals are known as the crystallites, from which the polycrystalline solid is made. Okay, now moving to the next slide. What is the difference between the crystalline and the polycrystalline? So polycrystalline solids are composed of many number of crystalline solids. Polycrystalline solids are actually made of crystalline solids. They are not same as crystalline solids. Crystalline solids or crystals have ordered structures and symmetry, as we have already studied, but the polycrystalline structures do not have the long range order. The long range order is being disrupted in the polycrystalline solids. You can see here in diagram, the particular arrangement is not followed in the complete 3D structure. There is different arrangement in different in the whole molecule, in the whole crystal. The next point is crystalline structure is uniform and has no boundaries, but polycrystalline structure differ from this. It do not has continuous structure and it has boundary between grains. Grains are the crystallites from which the polycrystalline solids are made. So they are also called as the grains. Okay, so they do not have a continuous structure and they have boundaries between the grains. The crystalline structure is hard to produce and it is rare in nature, in contrast to polycrystalline solids. The crystalline solids are very rare in nature, but the polycrystalline solids can be easily found. Okay, so I hope you have understood this topic. Now Thank you for watching.